All right, so for larger matrix, we're going to start by defining what the determinant is for an elementary matrix. Okay, so now remember there are three types of elementary matrices. Okay, so if an elementary matrix is obtained by switching two rows, then we're going to define that the determinant is going to be -1. So remember that the switching rows changed the sign of the determinant, and you can check for even for the elementary row obtained from for a 2 by 2 by switching to rows, then of course is going to be equal, the determinant is going to be equal to -1. So we're going to define that to be -1 for any elementary matrix obtained in that way. Is going to be k if the elementary row is going to be obtained by multiplying the ith row by k. Remember, that's one of the elementary operations. If that's the one we're using, then the determinant of the corresponding elementary matrix is going to be k, and it's going to be 1 if we use the third row operation, which, as you may remember, I hope you still do, I just said it a few minutes ago. That's because of the fact that when we add to a row a multiple of another row, that's not supposed to change the determinant, so we're going to leave it as a 1. Okay. Now, then what we're going to do is, if we're going to say if we have a matrix which is already in REF form, then the determinant is going to be given by the product of the elements on the diagonal. Okay. And finally, to obtain the determinant of any other square matrix, what we're going to do is the following. We're going to first of all change A to an REF form. So we're going to start from A and then multiply by one elementary matrix, another one, each of these corresponding to a row operation, and so on, until we arrive at some matrix which is in row echelon form. At this point, we're going to define the determinant so that it will preserve products. So that means we're going to define the determinant of A as the determinant of R divided by the products of the determinant of each of the elementary matrices. Now, if that sounds complicated, well, that just confirms what I was telling you earlier. Some of the computational and technical aspects of these determinants can be a little bit messy. However, in fact, computing them is not that complicated as long as you follow the main procedure, which is what I'm going to show you in a second. Before giving you an example to convince you of how this procedure is actually a lot simpler than it looks, let me point out a couple of technical points. First of all, in the definition, you may have noticed that the definition is based on row reduction and row echelon form, and you may remember that neither of these are unique. So I may arrive at different row echelon forms, and I may use different row operations. Well, it turns out that this definition does not depend on which row operation we use or which row echelon form we come up with. As long as you do it right, you will always come out with the same answer, and of course as long as they match. Of course, what you want to do is you want to use whatever row operation whatever row echelon form you obtained by using the row operations you are using in the formula, so they have to go together. But as long as you do that, the answer is always going to be the same. Also, notice that in practice, the way that we're going to compute these determinants is going to be a lot easier than the definition seems to suggest, because what we're going to do is we're going to do row operations, keep track of the effect they have on the determinant, and then compute the determinant as soon as we get an REF. The first REF we get, no matter how messy it is, as long as in REF, we multiply the diagonal elements, and having kept track of all the changes that the row operations made, that's going to give us the answer, and it's going to be the correct answer. Time for an example.